Good morning, Jocelyn.
Good morning.
Oh, I got that weird thing going on.
Oh, you got an echo.
I hate the echo, and I don't understand what does
Echo's
it.
cool, though.
Let me see what's up with the echo. Let's see. Oh, I know what I can do to fix that. It does that thing. I know what I pushed. I pushed the wrong button. There's a
Does
button.
anyone else just want to go back to bed, or is that just me?
I think it's just you.
Okay, it is just me.
Drew, come on.
Can't wait until Jules comes.
Drew, come on. Lily? All right. There you are. Where's Lil? She coming?
Lily, you need to do.
That should be better.
Lily,
Yay, the echo's gone.
Ever Junior lab rat.
She coming. So I see you got snow again, Jocelyn.
Yes,
That is crazy.
not that much snow, but enough snow to be able to go sledding down our hill.
Wow. That's wild. Snow, enough snow to go sledding down the hill. Oy. That's just crazy. Oh my word. I wonder if this share thing is so weird how I don't always get the, hang on. It's like I sometimes don't get the, what's the word I'm looking for? Oh my gosh, my brain can't function. The sound up there. I think I got to.
What is that video called? Because I want to show like my dad later.
Oh, you can just look up Bobcat. It's all over right now. It's Man Throws Bobcat. Because it's trending because it's just so crazy.
I mean, yeah, it looks fake at first, but then
It
when
does
you
look fake.
see the bobcat.
Yep.
Then you kind of know.
Well, when you see the Bobcat cross the street, it's kind of a giveaway that it's not fake, which is what's even weirder. Trying to see if I can get the sound up here better. I don't know why it does this. Sometimes it does sound and sometimes it just doesn't want to do it. So, it's not connecting. Of course it's not connecting. Let me give it one more second up there. And we're still waiting on Jules and Ella.
Not Jules. Drew. Guess what anime my mask is from?
I do not like.
He wouldn't know because he doesn't know which anime is which. So
It's from Totoro, my neighbor.
I'm sure it is.
Or my neighbor Totoro. I don't know anymore. I get that way.
I do not watch anime. I do not like it.
Why?
I don't.
unable to connect. Try again.
The plot, the
It's just-
design.
Just not a fan of anime. I don't like it.
Ah, doing it again. Hang on one sec, guys.
You
Sorry.
watch anime? You watch anime?
Jules does.
Yeah, Jules does.
Jules watches anime?
They bonded over anime.
Yeah, we sent for the same people too.
Mm-hmm. Did you decide if you're what you're doing next year yet?
I'm not allowed to go to public. I know that for sure.
Oh, you're not gonna go? Okay, I know
My
you're
dad
talking
won't
about
let
it.
me.
Your mom won't let you?
My dad won't.
Your
let
dad
me.
won't let you. Okay, well,
I've been begging every single day.
there you go.
It's middle school. So
Yeah, that was the worst for me.
I
Middle
wanna
school
know
was
what middle
the
school
worst,
was.
but it's okay.
It's either I'm going this year or next year.
Okay,
I'm
there's
gonna beg.
this. Hold on, I'm gonna try one more thing.
Yes, I want to know what middle school's like. It's horrible. I was back.
I remember when Cole hit middle school, he said that he thought he was missing out because he wanted a locker. And I was like, I will buy you a locker if that's what you think you're missing. I'll get that for you.
Hey, aren't there lockers?
Yeah, I mean, you can buy a locker. So if that's what he wanted, I would just get it for him. But
I have a locker downstairs in my grandparents' basement.
do you?
And
There you go.
To put like swimsuits in, and I just love it.
Sometimes I can get Jocelyn's voice or Senya, whoever's speaking, up on the screen, and it's so much easier to hear. So that's what I'm fighting with. If you guys bear with me just one more second. I will make it go.
I'm fine with that. I see this almost every morning here, so.
Yeah, I know. Usually it's good, but I wish we could hear them better. So
Because the volume's up so high, but yeah.
right. Okay, so it'll connect. It should connect this time. There it goes. We'll see if this makes it any better. If not, we'll just be like, oh well, we'll listen to her here.
Yeah, Miss Danny.
Yes.
So there was something really hard. So when COVID hit, like I was supposed to do my play thing
Yeah.
because I was in Frozen Junior, like a Frozen play.
Okay.
I couldn't do it because COVID hit. So
Right.
then I had to try to do it online.
That's pretty bad. Yeah.
Because the scripts are at theirs.
Oh,
When you didn't go to class, you can't remember choreography.
my niece did a play that we watched by live stream, and they did their best, but man, was it difficult because they were in Virginia and the rules there were really strict, and they had to wear masks on stage. We couldn't understand anything anybody was saying. There were no body mics. It was rough. Jocelyn, can you say something again? Anything? I'm just checking your mic.
Hi.
All right, she's still there. All right, so let's go ahead and start then. I guess the D'Antoni girls. Oh, here they come. I just got a notification on my phone. The ring.
Yay.
Mhm. All right. So last week we did nuclear chemistry, and this week we are starting what is basically organic chemistry. And organic chemistry is really any kind of compound that involves carbon. So it's all,
Everything.
pretty much that, well, that's a living thing, and it falls into certain groups. It's hydrocarbons, really.
Aren't trees basically made up of 100% carbon?
Not 100%, no, but
88%.
carbon makes up a lot of living things. If you're a carbon-based life form. Most life forms that you're familiar with are going to be carbon-based. Not everything, but most things. So I was saying earlier that I've had awful allergies this week, and my nose keeps running, and then I put my mask on and I get all this like condensation and I have to keep sniffling. So I may end up pulling it off a little bit. All right, so let me share my screen for you guys. You can see what we've got going today for our lesson. Here we go. Here come the D'Antoni girls. I heard the door.
Yep.
All right, so today we're doing compounds of carbon, names of structures and organic compounds and organic reactions. And this is in our last unit that's not our final, right? And so, hey girl,
They're really short.
oh my gosh, it's so
I like
cute.
it.
I love it. Do you like it?
Yes.
It's very cute. Looks like your mom. Awesome. We'll come have a seat. I like it. I think it's great. Actually, it looks a little like 11 once she gets her hair back. You know, like that's kind of the groove. Did you donate that? Because you had a ton.
No.
Wow.
I donated when I look like a girl from the 80s.
I know.
And I like it.
I told you.
Jocelyn, can you see Jules' new do? Can you
No.
kind of in the shade? Can you stand up and kind of lean into the light a little? Look at that. Look, it's so cute. It's short.
I like
Wow.
Very cute.
I like the style with the shades.
Excellent.
it.
So-
Why are my glasses indoors?
Today we're going to, all right, Drewy, you good? All right, so today we're going to go over these notes and we're going to go over our homework in class. You don't turn it in, right? I just need you to kind of contribute to class and you'll be good. And then we're going to do our lab. For lab today, Jocelyn, you need to know that we're making polymer balls, okay? One of your balls is going to work and the other one is, whoops, who just entered my waiting room, is just not going to work because when I got working on it, well, whoever that was came and left really fast. Okay. Anyway, one of them is not going to work. The one with the latex, the liquid latex that I bought way back when I bought all the supplies was too aqueous. It was too liquidy. And so when I tried to run the experiment and make sure it would work, it did not work. So if you have a home kit, like, hey, if you have a home kit like Jocelyn and Senya have, it's not going to work for you, but the other one will. So just complete the data based on the one that works. And also, I made a assignment sheet for you to complete, a lab sheet for you to write all your answers on and turn in. And it's in the assignment, it's attached to the assignment. So if you're not here today, it's attached to the assignment. If you are here, you can pick up a paper copy, okay? Because you do need to turn that in next week. All right, so let's roll. So compounds of carbon. So we have what are called allotropes. Does anybody remember what allotropes are from your reading?
No.
So allotropes are interesting. Probably the most classic one of all is carbon's 3 best known allotropes. It has more than 3, it has like 8, I think. But the best known 3 are, if you've got carbon in its most basic form, you've got graphite or coal, right? And then if you compress carbon for a really long time, what happens to it? Do you know? If you put coal under lots of pressure and heat, it turns to diamond. So basically, you've got dead bog plants, mostly like peat and ferns and maybe some dead dinosaurs, but definitely prehistoric plants, and they die and they turn into coal. And if the coal doesn't get mined and used, it gets deeper and deeper as, you know, sublimation happens and supposition happens and other layers build on top of it, and it gets under more and more pressure and heat, and it turns into diamond. So the same stuff that we use to burn for power and the same stuff you write with in your pencil, which is graphite, is the same stuff that a diamond is made of. It's the exact same chemical formula, it's just arranged differently. So that's what an allotrope is. So the properties of carbon allotropes depend upon the arrangement of atoms and how they bond together. So an allotrope is each of 2 or more different physical forms in which an element can exist. So graphite, charcoal, diamond, graphite, coal, diamond, these are all allotropes of carbon. Those are the best known ones, but there are lots of different elements that have allotropes. Carbon's the best known. So allotropy, that's the property that some chemicals have that allow them to exist in 2 or more different forms. So if a element has the property of allotropy, it will have allotropes. So obviously carbon, we can say carbon has the property of allotropy because it can be coal, graphite, and it can be diamond. So here are the ones that go with carbon actually. And some of these you've never heard of. So diamond, you know what a diamond is, right? Everybody knows what diamond is.
Yes.
Graphite,
Yes.
the stuff in your pencil. Yep, stuff in your pencil. Okay, and this one down here where it says amorphous carbon, morning Senya. Amorphous carbon, that's what we know as coal. Like coal miners go in there and, you know, go down into the mines and mine the coal.
Black
These other things here are different. Yeah, black lung, right. So this is this one can form on its own. I believe this one forms in space too, a lot too. So Lonsdaleite. And then you have these ones here. So this one, and this one are very often the ones that can be synthesized in a lab. So for example, if you look here, this is pretty cool. So a diamond, if you were to take that carbon, it's just pure carbon, it's going to be arranged like this. And doesn't that look like a pretty strong structure? I mean, look at that. That's a pretty strong structure, right? This is graphite, which makes sense because if you're writing with graphite, doesn't it kind of make sense that it would shear off as you write? You leave a little, you take a little bit off as you write on paper. If you scrub a diamond across paper, does anything come off? No, I mean, we use diamonds to cut glass and to cut metal, and we use diamond to cut other diamond because there's not much that's harder than diamond. And then this one right here is amorphous coal.
Wait,
Hmm.
what about steel?
Oh yeah, they use diamonds to cut steel. They,
Mhm.
Or to sand it. They'll use diamond dust and
There
they'll
are
use it as
certain
a
things
sander.
like what's it called? Well, for one, there's titanium that's stronger.
Mm.
What's it called? There's one other.
There's a couple. So if you look here at this one, this is what coal, tungsten, this is what coal looks like. If you were to look at coal in a mine, it's going to look like this. It's just kind of a mess, right? And that makes sense because it's kind of crumbly and it falls apart. And this stuff here, this Lonsdaleite, which is right here, this is stuff I said you can find in space. I think you can also find it in soot. But this one and this one and this one and this one, look at those. So these are things that can be synthesized. What does this one remind you of? Does this remind you of anything? It looks,
Soccer ball.
yeah, it's a soccer ball, isn't it? Jocelyn got it. It's a soccer ball. Looks just like a soccer ball. And this one is a tube, and it's a single-walled carbon nanotube, or they call it a Bucky tube. So these are things that scientists have found a use for, which is really kind of cool, a specific use for. So now we get to hydrocarbons. So what is a hydrocarbon? And a hydrocarbon is the simplest type of organic compound, and it only has 2 elements, carbon and hydrogen. They can be arranged in different ways, but that's all that's in it, okay? So for example, this is methane, ethane, and ethene, and this here is, this is one type of ethene, this is another type of ethene, but you can see that there's nothing there except carbon and hydrogen, right? No other elements are present. But look, you've got different compounds based on how they're arranged. And that's where organic chemistry is tricky, because it's all about how everything is arranged. It comes down to these things called functional groups, which we'll get to in a minute. So we have different types of hydrocarbons. You have these things called aliphatic hydrocarbons, and they are based on the chain of carbon atoms. And there are 3 types of aliphatic, all right? This is where it starts to get tricky. You have alkanes, you have alkenes, and you have alkynes. All right, now the difference is that alkanes have a single bond, a covalent bond. Alkenes have at least 1 carbon-carbon, and then alkynes have a carbon-carbon triple bond. So if you ever read the back of, this is a great example, but if you ever read the back of your shampoo bottle, you're gonna see things that have alkane, alkene, or alkyne as part of the name. So basically, this is like a root word. Like, say, take the word do, the verb do. You can undo, you can redo. What else could you do? You could probably, there are probably other versions of that. What's a good verb you can do stuff with? You can, or a good, huh?
Wait, never mind.
There's lots of verbs you can do that with, where you can put different prefixes and it changes the meaning of the verb, right? That's kind of how these are. This is like the root word. And then you can attach different extensions to it that tell you about the rest of it. So you know, if you see alkane in the middle of a word, that it's got a single covalent bond. And then you sometimes will have a hydrocarbon that's aliphatic. It's got a ring of carbon atoms. And those are called cycloalkynes. And so you've got cycloalkenes and cycloalkynes and cycloalkanes. Isn't this fun? This is why organic chemistry made my brain so tired, because you have to look at some random molecule and name it. And that's really, gets really, really challenging. So the other main type, so your first main type are your aliphatic hydrocarbons. Your second main type are your aromatic. Okay, now what's the word aromatic mean? You ever heard the word aromatic? How about aroma? That's part of it. You ever heard the word aroma? You've heard the word aroma.
Sounds like a language.
You might say, oh, these flowers have a lovely aroma. What does that mean?
Smell?
Yeah, smell, exactly. So these are benzene. We call these benzenes, okay? And they're flat ring systems. So their carbons are in a flat ring, like a hula hoop, okay? And they have overlapping, their p orbitals overlap. And the electrons in the benzene ring have got special properties that this is what makes them different from alkanes, alkynes, alkenes. So they used to call these aromatic because a lot of them have a really strong fragrance. But in modern chemistry, we've changed it. So aromatic doesn't have anything to do with smell when we're talking about chemistry. It has only to do with the fact that they have a very stable ring, which is typically this benzene ring. I'll show you a picture of one. So here's your flow chart. You have your hydrocarbons, and they're aliphatic. That'll be the word we use for them. And then over here, you have your, see, they put them here and said you have alicyclic. We're not really too worried about those. Aromatic. And I got to check. What's my check? Rewind, redo, reverse, report. Yes, there you go. Very good. So that's where you're using re. So Senya is using a prefix here. Rewind, redo, reverse, record, report. Yes, very good. Very, very good. So that's an example of when you get to these functional groups, you could have the functional group attached to an alkane, alkene, or an alkyne. And that would be like using re and then using a different word. Rewind, redo, reverse, right? That's interesting too. Interesting point. If you see, I do choir, right? Like for years, I've done music. If you see a word that has RE at the front, where it means to do something again, like redo, remake, rewind, reverse, then it's re. But if you see RE at the beginning of a word and it doesn't mean that, like the word redeemer, it's re. Now you know. Now you know. It's never redeemer, it's redeemer. Now you know.
I already knew that because one of my teachers always corrected everyone when they had to say like redeemer and stuff.
Good. Hey, smart
She
teacher.
wasn't the nicest teacher.
No, no, it wasn't. It wasn't. the
She
best.
liked correcting all the kids.
Oh, that's always fun. People who like correcting. All right, you girls paying
She was
attention?
really snappy with it.
Oh, I love snappy people who love to correct. So here's where the functional groups come in that I was talking about. So your functional groups. All right. These are kind of fun. We're not going to have to memorize them or do anything with them, but know that they're there because it is kind of like, think about Mr. Potato Head, where you could stick on a new nose or stick on a new eye, and you can just change how he looks by continuously sticking on different pieces. That's exactly what these are. These can attach to, see, here's your alkane, alkene, alkyne, and all of these different things can kind of pop on, and it completely changes the molecule. So it's really kind of neat. So organic compounds are classified by their functional group. And that's the main thing I want you to know. These same functional groups here have similar properties. And so they'll undergo similar reactions regardless of whether it's an alkane, an alkene, or an alkyne. And so when it gets to naming them, you kind of have to learn what all of these different functional groups do. So that if you see it attached to something, you know what it's going to cause that molecule, how that molecule is going to behave. If you ever go into like pharmacology or something, medicine making, that's really, it's really involved. So they functionalize the compound. That's where we get the term functional group from. And they undergo the same type of reactions, which is what I was saying, and they can be used to distinguish similar compounds. So names and structures. All right, we aren't going to memorize these, but I want you to know that it's a thing. Okay, here's how you name them, because it gets really, like I said, this was brain pain for me. Brain pain. So the names of alkanes, actually alkanes, alkynes, are the basis of the names for most hydrocarbons. So you take the root, and then you do that by identifying your longest chain here. And then you find the root name for the number of carbons in the chain, and then you add the suffix, which in this case is ane. So this one's actually hexane, because it has 6 carbons, which makes it a hex, and then it's ane, so it's a hexane. So here's an example, just to show you how complicated it gets. Yeah, we're not going to get too much into it. I know, I'm gonna make it a little bigger, but just to show you, because I want you to understand how complicated and how complex it is. So, for example, if you undergo certain reactions, you can change an alkene to an alkane, or an amine in the presence of an acid will become an ammonium salt. And then you've got all these little notes, but this could happen, or that could happen. Gets really, really complex. You've got your esters, you've got here's an alkene. And if your alkene is in contact with acid and water, it'll become an alcohol. And if your alkene is in contact with just a strong acid, it becomes an alkyl halide, and it gets really complex. And then you have all of these guys here. Here are your names, here are your functional groups, and this is how they're written. And so like here are their names. So here you have an aldehyde, you pop on this functional group, that goes right here, and then it becomes pentanol. It gets really complex. But there are people who live for that level of complex. I'm not one of them, but it's really neat, right? I mean, their entire classes, you can take years and years and years of organic chemistry. It gets really, really involved. So,
Name's Danny.
uh-huh.
There's this TV show I was watching when my mom thought it was just like a little like 5-year-old learning science stuff.
Uh-huh.
It was actually like your science version of stuff.
Oh, cool.
And so I actually kind of just watched an episode yesterday about like all of this stuff.
What was the show?
I can't remember the name of it right now, but it was either on Netflix or Spectrum.
Excellent. When I was a kid, I used to be addicted to Mr. Wizard. Mr. Wizard is amazing. I still have like all of his DVDs. He was this Canadian dude who there was nothing creepy about this, by the way, in the 80s, but he brought neighborhood kids over to his house one-on-one and did science experiments with them, which now people would be like, why does that old man have that child in his house? But then it was just kind of what he did. He was like the neighborhood, everybody loved him, and everybody went to his house and they did science experiments.
He was kind of like the neighborhood teacher.
Yeah, he was the neighborhood teacher. So for modeling, all right, so there are different ways to model these organic compounds, and they've all got advantages. So here are examples. So you got this one called a structural formula. So the advantage of this one, as you can probably see, is that you can very clearly see how many carbons you have, how many hydrogens you have, and you can count them, right? See, if I asked you how many carbons were in this, you go, oh, 2 right there, right? So if you need to write a chemical formula, these are great. You can look at this and go, oh, C2H6. That makes perfect sense. Then you got this ball and stick. So what would be the advantage of this? What do you think? Yeah, it's about the geometry. How are they arranged? Because if you look at this, this is very one-dimensional, right? It's not flat like a dinner plate. It actually looks like that. It's like a little pyramid with a little chimney on top. So you have to know that when you're looking at this, it's not a true representation of how the molecule actually looks. And how it looks says a lot about how it functions. And then you have these space-filled models, which try and give you an idea of where the electrons are spinning. So then we have our reactions, and oh, do we have lots of them. But today in lab, we're going to be dealing with polymers, all right? And Senya, I was saying before you came in, I think, that one of your balls for your polymer lab will do perfectly and the other one will not. The latex that I got initially was too aqueous. It was too liquidy, too runny, and it didn't do what it was supposed to do. So I ended up having to run out last night and find more. So your latex one won't work. So just complete your lab with the other polymer, which is the sodium silicate.
Lab 30?
Yeah, lab 30. And then I put a digital copy of that lab, attached it to the lab online that is just a sheet to complete. And that's all you have to complete. So get the lab, I'll put it in the email, but get that sheet and finish that. And everybody who's here can just use the copies I have. So
So don't
polymer.
use the latex?
Yeah, the latex one you can try, but it's not going to work. So it just won't.
Okay.
It was a bummer. I was trying to do it. I tried everything, trying to modify it. It did not work. So a polymer is a large molecule made up of chains or rings of repeating subunits called monomers. So they have high melting points and boiling points. And because molecules consist of many monomers, polymers tend to have high molecular mass. So they're heavy as molecules. So this word polymer comes from Greek, poly, which means many, right? And then you have suffix mer, which means parts. So here's where your Greek and Latin come in again in science. So it has many parts. And that was coined by the Swedish guy named Jöns Jakob Berzelius, and I'm going to get it wrong. Yep. And then
That's a tongue twister.
yeah, it is, in 1833. And he had a slightly different definition at the time. So the modern understanding of polymers is we call them macromolecules. All right, there's another prefix. What's macro mean?
Small?
Nope.
No, large.
Large. Macro means large. Micro means small. So they're macromolecules. They're large molecules. And that is the definition proposed by this German organic chemist named Hermann Staudinger. And so that was 1920. So a little over 100 years later, they kind of refined the definition, which you see happens a lot in science, right? We change the definition, we change how things, how things are described based on how they really function rather than what was initially discovered. So if you look at the picture here, this is a perfect example of a polymer. Look at the long, long, long chain. See how long that molecule is? That's a long molecule. And if you Google polymer, you'll see like there are graphics of big, long molecules like H. Look at this one here. See how long that is? Lots of H's, lots of C's, lots of O's in there. Big, long.
That's long.
Yeah, it is. See there. And then it says you have a first coded byte. They break it down. Cleavable space, chop. Meaning this particular molecule can break right here when it's reacting. And another, call it a coded byte here and a coded byte here. So these are like individual pieces that make up one big long chain. And then you see this big long one here, right? So again, if you were to get into organic chemistry a lot, you'd see a lot of this kind of stuff. So the things that can happen in reactions with hydrocarbons are substitution, which this makes perfect sense. One atom replaces, or a group replaces another one, right? We've had this similar kind of thing with other chemical reactions, right? Sorry. You can also have addition, same idea. You add one, right? It makes perfect sense. And then you can also have elimination. And that makes sense too. Somebody leaves. That's pretty much what happens with them. We aren't going to get too in depth with them because they're like I said, it's another course all in and of itself. But this one, I want you to know, condensation. What does condensation mean to you when you hear the word? What do you think of?
Like the stuff on the outside.
Yeah, what did you say, Senya? Don't know. Drew says
No.
like the stuff on the outside of your glass. Yeah, I actually have a little bit on the outside. My drink is cold, so I have a little, it's a little damp right there on the outside. So what does that mean? Why does that happen? Do you remember when we did
It's the cold air around.
phases of matter? Condensation happens when what? A gas becomes a liquid, right? So when a gas becomes a liquid, it condenses, right? You can condense your fuel for the grill and make it liquid in the big tank that you pick up, right? And you have water in the atmosphere that condenses on the outside of your ice cold glass, right? Well, condensation, when we're talking about chemical reactions, is sort of related, but not the same. Condensation has to do with water, and it has to do with forming water. So if you can think about when you have water on the outside of your ice cold glass, and we know that's condensation, that water didn't form really. It was already there. It was in the air. It's just it condensed together, collected, and now you can see it, right? Little individual or little, bunches of water here and there came together and made big bunches of water, so big that you could see it. In this case, we actually are going to form the water. And we call it condensation because we have formed water. So if you ever see anything where you've got a water hanging out, it's condensation. That's what it is. And that's important to know because you don't want to get this condensation confused with the phase change condensation. So I would like to know if you guys have your homework out. I want everybody to tell me something they've learned. So we had an assignment this week to research a particular inventor, a scientist.
Kevlar.
And she invented, I gave away gender already. Okay, this scientist invented Kevlar. So I would love to know if anybody has the name of the scientist first. Anybody who wants to share?
I named the York Times because
Oh, this is on my way to questions.
Well, we're not handing weekly questions in. They should be here.
Oh.
So you can answer them. All right, so who knows the name of the scientist? All right, what did you get, Eleanor? Stephanie, yep.
Stephanie.
Yeah, it's weird. Kowalik, yep.
Wow.
All right, Stephanie Kowalik, very good. And, well, hand it back to him if you see it, if it's this week's questions. All right, and in what year did she invent Kevlar? Do you know? What'd you get, Ella?
1965.
Oh, Jules beat you, 1965. All right, so 1964, right around in there. All right, so Ella, what do you have for the next question? What was her goal? Yeah, so she was looking to invent a super strong fiber, right? So that was her job. She was tasked for this job to invent the super strong fiber. And what was it for, did you say? For performing under extreme conditions. Okay, there's all kinds of extreme conditions. Think about the ropes and stuff that they use on like fishing ships, right? So she was trying to come up with something. And then, so what I've got is that it was not only just strong, but also lightweight. And they wanted to replace the steel that's used in tires because steel was at the time put in bands inside tires. They were trying to find something else. What'd you say her company was, Lily? Huh? DuPont. All right. What do we know about DuPont? Who knows anything about DuPont? Anybody know anything about DuPont? What they make, what they do? Did somebody say something? So DuPont makes everything. DuPont is a huge industrial company. They do a lot of industrial chemistry, kind of like 3M. See, he's got the same allergies I have. We both been like, oh. So DuPont makes paint. You may have seen DuPont paint before. Now you get the hiccups. DuPont makes plastics, all kinds of stuff. And you would probably recognize their logo. Also, DuPont, you guys good over there?
Yeah.
So DuPont was this was one of these companies owned by a family that got super wealthy. So you may find buildings on college campuses named DuPont because these people gave a lot of money. We actually had one at Hollins. The chapel is a DuPont chapel. So they were very big in philanthropy. All right, so let's see, Drew, you do the next one, and then I'll let the online folks do the last three, because that's perfect. So did she win any awards for this invention?
Yes.
Yeah, okay. Can you give an example of one, Drew? Do you see any, or did you write me down, or no?
I didn't write it. I just said yes.
Okay.
Actually, wait, no, I did.
You did? What'd you write?
Um,
He's looking.
oh,
No.
no, that was.
Well, here's an example. I threw a lot of them down. So any of these, I mean, look at this.
She won something for like a. I think she won like employee of the.
Yeah, she won a lot of awards at DuPont. So she received Chemical Pioneer Award from the American Institute of Chemists, an award for creative invention from American Chemical Society. She was added to the National Inventors Hall of Fame. She received a National Medal of Technology and the IRI Achievement Award. She received a Perkins Medal from the American Chemical Society, and she was inducted into the National Women's Hall of Fame. She also was awarded honorary degrees, which means you don't go to that school, but they're going to give you a degree anyway, from Carnegie Mellon and Worcester Polytech and Clarkson University. The Royal Society of Chemistry grants a biennial, which means every other year, Stephanie Kwolek Award to recognize exceptional contributions to the area of materials chemistry. And she was featured as one of the Royal Society of Chemists 175 Faces in Chemistry. I think, I may be wrong, but I thought she got the Lavoisier medal too, which is like the big one. So yeah, she did a lot, a whole lot. All right, so whoop, I didn't mean to do that one. So let's see, Senya or Jocelyn, or I don't know where Sky went. If one of y'all can tell me if you and this chemist have been alive at the same time, and if you are still.
No.
Like, when did this happen? Hang on, Drew, let them answer. Anybody want to go, Senya? Jocelyn, Sky, nobody? How about one of y'all here? Have you-
Yes.
Yes, you have. So she was born in 1923, but she died in 2014, which was not that
I
long
was
ago.
born in 2010.
Yep, so you guys were born, 2010, 2008, 2012, wherever, but most of you have been alive, I think all of you here, have been alive the same time as Stephanie Kwolek. All right, and then Jocelyn or Senya or Sky, do any of you have any answers for the last question?
Sky isn't here anymore.
Yes, she is.
Oh wait, I'm too confused.
You're thinking Alec. Anybody? Wow, they disappeared right when I'm asking them questions, goobers. All right, so who has some, guys, keep it down. So who has some applications of Kevlar? Who wants to share? Any applications of Kevlar? Drew, what are applications of Kevlar? You tell me something. Ella, you go. I meant Ella go first. She put her hand up. What'd you get?
Boats, planes, body armor, bulletproof vests, golf clubs, and bicycles.
There you go. Boats, planes, body armor, bulletproof vests. Would you say golf clubs and what? Bicycles? There you go. What else do you have? Anything different?
I put Kevlar vests, helmets, and Mark Rober's trampoline.
Mark Rober's trampoline. Okay, there you go. So yeah, lots of stuff, but probably best known for bulletproof and bomb-proof metals. Armor and materials to keep people safe. And it says,
So police officers wear.
here that has more than 200 applications, including tennis rackets, skis, parachutes, boats, airplanes, ropes, cables, bulletproof vests, car tires, firefighter boots, hockey sticks, cut-resistant gloves, armored cars, protective building materials like bomb-proof materials, hurricane-safe rooms, bridge reinforcements. During the week of Kowalek's death, the 1 millionth bullet resistance vest was made with Kevlar and sold. Kevlar is also used to build cell phones, like this particular Motorola has a Kevlar body. So that's pretty fascinating. So I wanted to show you what.
Miss
his
Danny,
whole-
I have a few.
Oh, there you're back. Oh, what do you have? Anything we didn't say or?
I have this is might be weird. Car brakes
Okay, brakes.
are
All right.
also
Mhm.
and boats and body armor and bulletproof vests.
Yes,
That's
very good.
what I read.
So this is Stephanie Kwolek, and it's a very short video, but it's really cool because you get to kind of meet her, get a feel for the kind of person she was. I think sometimes we think of super smart scientists as being kind of aloof and maybe unapproachable. She looks like somebody's cool aunt to me. Like I would totally have, sandwiches and coffee with her or whatever. So here she
Sandwiches
is,
and coffee?
whatever she's serving, or I'm serving.
love about my work is that I have the opportunity to be creative every day. I love the excitement. There's something about me, it's an inherent part of me that wants the excitement of invention and creativity. My schooling was somewhat different from what it is today because we had 2 classes in one room. This was in a public school. Frequently, you'd finish your work and you would hear where someone was having trouble in the next class. You would put up your hand and you would give the answer, especially in math. And this went over like a lead balloon, I tell you. But what you really did was you learned 2 grades at one time. I
All right, I was gonna go tell them to not be so loud.
was learning and loved learning new things. I find it very exciting. So this probably made me what I am today and what I was for many years. When I entered the workforce in 1946, not many women were being hired, but the few that were, they were hired because there were so few men available. They were at war or just coming back from war. So women were being made offers, but that didn't mean, that the problem was completely solved because women had a very difficult time after they got jobs. And many women did not stay very long. But I was stubborn. And I decided that I was gonna stick it out and see what happened. And things improved eventually. But I didn't stay just because I was stubborn. I stayed because the work was what I wanted to do. It was 1965 and I was assigned to look for this super strong, super stiff, but lightweight fiber. In the course of that work, I made a discovery. The results came back. It was very strong and very stiff. And like anything we had made before, I hesitated about telling it because it was unusual and I didn't want to be foolish. And so I sent it down a few more times and it always came back more or less the same numbers. And so I then told my supervisor and we in turn told the laboratory and everybody became very excited. So that was the beginning of Kevlar. I was elated to have made this discovery because most people work a lifetime and they never do anything like this, something that saves human lives. I think the role of science is to improve human life in general and improve the world as well. When I reflect back upon my career, I am inspired by the fact that I was able to do something that was of benefit to mankind.
She's pretty darn cool. I really like her. She's awesome. All right, so I had one more video, but we're gonna be at it. All right, Stephanie, we like you, but that's good. I had one more video, but we're not gonna have time to watch it, so I'll put it in the email. But it's
Oh my
about
gosh, what is that?
it's about Mad Hatters.
I don't like that.
And
I don't like that.
What is a Mad Hatter? You know the Mad Hatter, Drew Hush. You know the Mad Hatter, right? So there's a saying, he's mad as a hatter, and that has to do with a particular type of we don't have time for it, but I'll put it in the email so that you guys can watch that. I'm going to hand out some papers that I need to get back to you. And so remember, if you are not here today and you're doing the lab at home, the latex isn't going to work for you. So just do the sodium silicate part of the lab and go ahead and answer the questions on the sheet that I attached to the lab in Teacher Ease. Okay. And I think everybody answered questions except I didn't get any answers from Jocelyn or but you already sent me your homework, so I saw it. So I'll need Sky's. And then I think we are good. We only have 4 more classes, y'all. Can you believe that? We are nearing the end. Okay, so I'm gonna hand this out for you guys and we'll say goodbye to these ladies for now. Later, ladies. We will see you later.
Bye.
Bye.
Bye. All right, I'm gonna end this Zoom. We're gonna start